It often happens in linear algebra in which opposite changes balance out. For example, consider 6 into 5. We can write it like this because 1 is multiplicative identity. We can write 1 as 1 by 3 into 3. This is written by associative law. Here 6 changes to 2 and 3 changes to 15. We can do similar thing in operator vector multiplication. Instead of taking multiplicative identity, here we will take identity matrix. When we change the basis of the vector space, the components of vectors and operators transform in a way to preserve operators' action on vectors. You can also understand it with this example. If gram is changed to kilogram, then 1000 will be changed to 1 to balance out the change and give the same quantity. Vectors are contravariant and operators are covariant. Here are some properties of transpose operation. From now on, we will call covector to row matrix operator. Variables and arbitrary constant can interchange their roles without affecting the result. We can visualize vector v in vector space and covector psi in covector space. But what if covector psi was also a vector in vector space? A number is just a measurement of something. How much of something is there compared to the unit of measurement? So what does the number we get by covector vector product measures? Just like a ruler measures different lengths of different objects, covector measures different vectors. There are many vectors whose measures are equal. We can plot a 3D graph between vectors and their measurements. But this idea won't work for 3D vectors and their measurements. We can solve this problem using contour lines, which are used in cartography. Let's make curves of constant measures of distinct vectors that are measured equally with the same measurement levels. Covector vector product of psi v gives a constant c, which is a function of x and y. For 2D vector measurements, the contour line is a straight line. In this graph, vector psi makes an angle theta with the x-axis. The components of vector psi are a, b. Therefore, a equals projection of vector psi on x-axis, which is psi cos theta, which gives the value of cos theta. Cos theta can also be found by that little triangle made by projection of I hat on vector psi, which implies projection of vector psi on x-axis is equal to length of psi times projection of I hat on psi vector. We can get similar result for projection of vector psi on y-axis. We know that covector psi is row matrix with components AB. Writing the values of AB we derived earlier, which gives us this result. Since psi covector is linear, we can write psi v like this and get this using our previous results. Projection operator is also linear, so we can write it like this. Hence, applying 2D covector psi on a 2D vector v is equal to the projection of vector v on vector psi times the length of vector psi. We can generalize this result. This is the reason why control lines are parallel to each other. When vector v is perpendicular to vector psi, vector v's projection on psi is 0, which means all vectors lying on this blue line are measured to be 0 by covector psi, which means contour lines are perpendicular to vector psi. This is the reason why covectors line have increasing values as you go away from the origin. This is why vectors and covectors are dual of each other. Duality is not only geometric but also algebraic, which can be generalized and abstracted. Similar to transformation of vectors, we can transform covectors. We can interpret matrix A is collection of covectors, and this transformation is psi1 psi2 being transformed to 1D covectors omega 1 omega 2.